Unit 5. Positive Displacement Pumps. There are many types of positive displacement pumps. The ones this course will cover are those most commonly used in wastewater treatment plants. The positive displacement pumps covered in this course are the plunger pump, the diaphragm pump, the progressing cavity pump, the screw pump, the peristaltic pump, and the rotary lobe pump. The progressing cavity and the screw are two types of mechanical action that can move liquid through the pump. This course will also briefly consider the airlift pump. While it is not a positive displacement pump, it is included here to complete the discussion of the more commonly used types of pumps in a wastewater treatment plant. Plunger pumps. Let's begin with the plunger pump. The plunger pump is a positive displacement pump that uses a plunger or piston to force liquid from the suction side to the discharge side of the pump. In the wastewater treatment plant, the plunger pump is most often used to pump heavy sludge. Let's start with the basic valve on both the suction and discharge sides of the pump. The check valve may simply be a ball. The check valve keeps the liquid moving in the desired direction. The plunger or piston moves up and down or back and forth horizontally in the cylinder. The plunger is moving upward on the fill portion of the stroke, which creates an area of lower pressure within the pump. This action opens the suction check valve, allowing liquid to enter the pump, and closes the discharge valve, preventing liquid from coming back into the pump from the discharge piping. Now, see what happens in the discharge cycle. The plunger drops, the ball valves reverse, and fluid is pushed into the discharge pipe. The movement of the plunger or piston inside the pump creates pressure inside the pump. So this kind of pump must never be operated against a closed discharge valve. All discharge valves must be opened before the pump is started to prevent any buildup of pressure that could damage the pump. There is force exerted during the suction cycle as well, so the suction valve should always be left at least partly open. Now let's look at the major components of the plunger pump. Here is a more detailed diagram of the plunger pump. The suction line, discharge line, the suction check valve, the discharge check valve, and the piston or plunger are highlighted. Also included on this pump are two air chambers, the connecting rod for the plunger, and the packing. In the plunger positive displacement pump, there is always an air chamber on the discharge side of the pump. Frequently, one is on the suction side as well, especially if there is a positive suction head or if the suction lift is high. The purpose of the air chamber is to provide a cushion to smooth out the surges that occur within this pumping system. If liquid fills these air chambers, they can be drained by opening the tap at the bottom of the chamber and the air vent at the top. Now, the photo showing a check valve on a plunger pump installation. The arrow points to the location of the check valve chamber. This diagram shows the detail of a ball valve. As indicated, the ball normally rests on the valve seat. If the valve seat shows signs of excessive wear, it should be replaced. The valve gasket, too, can be replaced if leakage occurs at this point. There are guides within the valve chamber to guide the ball as it moves up and down in the suction and discharge cycles of the pump. The balls themselves will wear and will eventually have to be changed. If they are wearing too rapidly, talk to the manufacturer to obtain balls made of more durable materials. Replacing the valve seat and gasket or the ball requires access to the ball valve chamber. The type of ball valve determines how to gain access. Specifically, before opening the ball valve chamber, be sure that the pump is shut off, locked out, and tagged. Then isolate the pump by closing the suction and discharge valves. If the pump isn't isolated, fluid in the lines will run out through the chamber. Relieve the pressure inside the pump by draining it so that fluid does not flow out of the ball valve chamber when it is opened. Let's look at some more. The compression ring is the same as in a centrifugal pump and is attached to the body of the pump by gland nuts. Any sludge that leaks through the packing into the trough is removed through the drain pipe. The two plugs shown in the pump body are not the same as those in the bottom of the air chambers. If the pump is clogged, it can be rotted through these plugs. The packing in the plunger pump is similar to the packing in the centrifugal pump, except that the lantern ring and seal water are not usually provided. In the plunger pump, A small amount of leakage is usually permitted so that any abrasive particles that get between the packing and the plunger eventually work their way to the top of the stuffing box where they can be flushed away. When the packing is new, it is good to loosen the packing slightly after the pump is in operation. Add oil and retighten the gland bolts. Do this 3 or 4 times at 15-minute intervals to set the packing properly. As the packing becomes worn, there can be excessive leakage of sludge around the plunger. This can be compensated for by adjusting the packing gland bolts. Remember to do this evenly, tightening each bolt a little bit at a time. The procedure for changing packing is similar to that for centrifugal pumps. Be sure to refer to the appropriate procedure when changing the packing in a pump. The plunger itself can become worn to an hourglass shape like this. How long a plunger will last depends on the corrosive and abrasive nature of the fluid being pumped. If the wear on the plunger or piston is 2.5 millimeters, 3/32 inch, or less on the diameter, it can be remachined. This could involve either spray welding or machining the plunger to the proper size, or resleeving the cylinder. If the wear is greater than 2.5 millimeters, 3/32 inch, a new plunger or piston should be installed. Now let's see how it shows a typical plunger pump motor and the first V-belt pulley arrangement. The motor speed is reduced to about 50 RPM, or 50 plunger strokes per minute. The first pulley system provides about half of the motor speed reduction. This pulley system transmits its torque to another pulley system. The exact method of speed reduction in each system may look somewhat different. The 2 pulley systems could be in a different configuration, or a series of gears could be used. We should also note that both shafts shown in the photographs are supported by 2 bearings, one at each end. These bearings should be maintained and replaced in accordance with the manufacturer's instructions. Now let's see how the rotation of the shaft causes movement of the plunger within the pump. This diagram shows the detail of the shaft and its connections to the plunger. The shaft is connected to 2 flanges, A and B. These flanges are driven by the shaft. An eccentric C is attached to these flanges with a stud, D, and a shear pin, E. As this assembly rotates, the eccentric moves up and down. Part F is the top of the connecting rod, and it is connected at the bottom at G with bolts and shims, in a way that allows movement between the eccentric and connecting rod assembly. The shaft, flange, and eccentric rotation cause the connecting rod to move up and down. Note the slots in eccentric C. Both the stud at H and the shaft travel in these slots in the eccentric as it rotates. Now look at the lower part of the connecting rod. The bottom is connected to the plunger J by a plunger crosshead pin I at location K and a bushing at L. Also, a piston guide prevents the piston from rocking as it moves up and down. This is how the rotational motion of the shaft is changed into the up and down motion of the plunger. The flanges are attached to and driven by the shaft. An eccentric is connected to these flanges so that it moves up and down as the assembly rotates. This eccentric is connected by a connecting rod to the plunger, causing the plunger to move up and down as the shaft rotates. The up and down distance that this connecting rod travels can be changed. This is done by changing the position of the shear pin. Moving the shear pin into one of the holes closer to the shaft will shorten the length of the stroke. This means that the plunger will not move as far, so the output of the pump will be reduced. In other words, this pin, besides acting as a shear pin, also controls the pump capacity. The connecting rod and eccentric must move freely. That focuses our attention on another important component of the plunger or piston pump. The oiler lubricates the surface between the eccentric and the connecting rod. As seen in the photo, the oiler usually is located on top of a bearing, referred to as a babbitt bearing. Another important component of the plunger or piston pump is the seal. It is the location of the seal that determines whether a pump is a plunger pump or a piston pump. The plunger pump has packing near the top of the pump, while a piston pump has an internal seal. Gauges and pressure relief devices are 2 other important components of the plunger and piston positive displacement pump systems. In discussing these two components, keep in mind that these pumps are often used to pump sludge. While the positive displacement type of pump does not clog easily because the back and forth movement of the piston or plunger tends to break up potential blockages, some problems still arise. Let's consider the gauges first. Accurate pressure readings provide important information about what is happening in the system. Conventional pressure and vacuum gauges are not usually operable for any long period of time in a sludge pumping system. The gauge passageways clog with hardened sludge, and the gauges fail because of high pressure surges. If conventional gauges are used, it is recommended that shutoff valves be installed at the gauge inlet to be opened only when readings are being recorded. A diaphragm-type gauge is recommended for plunger pumps handling sludge. This type of gauge has a diaphragm between the pressure sensing line and the gauge mechanism. This helps keep sludge out of the gauge, but the sensing line must still be kept clean. This diagram shows a better arrangement because the sensing mechanism is isolated from the sludge. Increases in pressure inside the line increase the pressure on the oil, causing a higher reading on the gauge. Pressure relief devices are extremely important on any positive displacement pump. These devices can save considerable cost and damage to pump system equipment because of blocked flows and high pressure buildups. If excessive pressure buildup occurs, the eccentric flange shear pin will fail, or a discharge pressure switch will open to shut off the driver. While the shear pin and the driver shutoff device should provide adequate protection, if they do not, the pressure relief device becomes important. The pressure relief device should be connected so that if it does blow, the pump will shut off and an alarm will sound. If the device does blow up, the operator will have to replace or clean and rebuild the pressure relief device, as well as clean out the line that caused the problem. This photo shows a ruptured disc, which is one way of providing pressure relief. As shown, the device is a disc between two flanges in the bypass line, which is directed, for example, to the primary line. If pressure builds up to a certain point, the disc will rupture and allow liquid into the bypass line. The bypass can be piped back to the suction side of the pump or away to some other point. Relief devices can be reliable if they are properly maintained and tested frequently to be sure that they are clear. If a relief device becomes clogged, it may become inoperative. To overcome sludge buildup within the valve or piping, the assembly should have provisions for flushing with fresh water to be sure that it remains operable. Operational characteristics of the plunger pump. First of all, plunger pumps are self-priming, and they can generally handle suction lifts of 4 1/2 to 6 meters, 15 to 20 feet. Even so, a positive suction head is normally provided. Plunger pumps can pump against up to 90 meters, 300 foot, of total dynamic head. The capacity of the plunger pump depends upon the diameter of the plunger and the length of the stroke. The capacity also depends on whether the pump has one plunger, simplex, two plungers, duplex, or three plungers, triplex. Using these parameters, the volume of liquid pumped with each stroke can be calculated and equals the square of the radius in millimeters multiplied by the stroke length in millimeters divided by 318,000, a conversion constant. In English units, volume in gallons per stroke equals r squared times height over 73.5, where r equals radius in inches, h equals stroke in inches, and 73.5 is a constant that allows use of inches in the calculation. Here is an example of how to calculate the capacity of a 50 RPM duplex pump with a 200 millimeter 8-inch stroke and a 130 millimeter 5-inch diameter plunger. The radius, r, is 1/2 the diameter. So, r equals 130 divided by 2 equals 65 millimeters. Again, volume divided by stroke equals r squared times h over 318,000. Plugging in the numbers, volume per stroke equals 65 times 65 times 200 divided by 318,000 equals 2.66, liters per stroke. Since the pump in the example is a duplex pump, it will have 2 strokes per revolution. At 50 RPM times 2 strokes per revolution, the pump will complete 100 strokes per minute. To find the capacity of a pump, we must multiply the volume per stroke that we calculated by the number of strokes per minute. The pump capacity is 266 liters per minute. The shear pin, which we discussed earlier, has another very important purpose. The primary function of the shear pin is to brake to protect the pump from damage in the case of a sudden overload. 3 of the most common causes of sudden overload and shear pin failure are a solid object lodged under the piston, a clogged discharge line, or a stuck or wedged valve. When a shear pin breaks, determine and remedy the cause of the failure before inserting a new pin and starting the drive in operation. When installing a new shear pin, make sure that it is of the proper size and select the lowest strength which will not break under the unit's normal load. If necked shear pins are used, be sure that the neck down portion is properly positioned with respect to the shearing surface, as in the diagram. Note too that the shear pins used should be ones provided or recommended by your pump manufacturer. There should be an adequate supply of spares. As mentioned earlier, an important operational aspect of any positive displacement pump is the proper control of valving when the pump is operating. All equipment operators must be thoroughly familiar with the valving arrangement so that no discharge valve is closed before another valve is opened. This point is extremely important since considerable damage can result if the pump works against a closed isolation valve, even for a short time. It is a good idea to make all changes in valve settings with the pump shut down. Frequently, pumps can operate from 2 sources or deliver to separate tanks at different times. In these cases, if the pump is not shut down during valve changes, there is a danger that during the changeover, all suction valves or all discharge valves may be closed for a few seconds and cause damage in the pump system. Another condition to look out for during normal operation of the plunger pump is partial blocking of the discharge piping, which increases the pressure. This may open the pressure relief valve, or break the shear pin, or damage the pump or piping, or cause belt slippage. One source of information that can alert the operator to the possibility of blockages building up is the record of pressure and ammeter readings. Again, take and record ammeter readings on each pump on a regular basis. There should be a built-in ammeter for each pump. If they are not present in the system, the operator should consider having them installed. As previously indicated, either gradual or sudden increase in ammeter readings for a positive displacement pump could indicate a blockage in the discharge piping. However, there are other factors which can cause changes in ammeter readings. Increases in ammeter readings for a pump could indicate motor problems, increased friction at bearings, heavier sludge being pumped, or simply aging of the equipment if the increase is extremely gradual. It may be difficult to determine the exact cause of an increase in ammeter readings. However, you can always anticipate that problems are probably just around the corner if the motor starts to draw more electrical current than normal. There are a few important points regarding the initial startup of a plunger pump. First, the direction of rotation of the pump should be checked to be sure that it conforms with the directional arrow on the driving flange. Notice the arrow on the flange in the picture. Before checking the rotation using the motor, it is a good idea, once the unit has been locked out, to turn the pump shaft at least 1 revolution by hand to make sure that the pump is free of obstructions. Be aware that the connecting rod may require adjustment during the initial weeks of operation of the plunger pump. Brass shims are installed between the halves of the connecting rod. These are removed to take up wear in the babbitt bearing. During the first few weeks of operation, the connecting rod should be checked regularly to maintain 0.13 millimeter 5/1000th inch clearance between the babbitt bearing and the eccentric. Also, during this period, the oiler should be set to lubricate freely at 5 to 6 drops a minute, rather than the 2 drops per minute usually required later. If the connecting rod runs hot, check the oil feed and clearance, and add shims as required. Excessive clearance can be eliminated by removing shims. Maintenance of the plunger pump. Now let's spend a few minutes considering important maintenance requirements of the plunger pump. As with all equipment at the plant, the main guide to proper maintenance is the manufacturer's literature. In general, the major maintenance requirements will be in the form of pump packing and proper lubrication of the pump. As packing becomes worn, there will be excessive leakage of sludge or water around the plunger. Normally, this can be compensated for by tightening the packing gland to maintain only a slight amount of leakage. However, when there is no further take-up available in the gland, the packing will have to be replaced. Refer to the manufacturer's instructions and to the information in the previous section on replacing packing in a centrifugal pump. The procedure is very similar for plunger pumps. Lubrication of the plunger pump will have to be done in accordance with your manufacturer's specifications and schedule. Here are some of the points of the plunger pump that will require lubrication. 1. Eccentric connecting rod. As shown earlier, there is an oiler mounted on top of the eccentric to provide adequate lubrication to the connecting rod eccentric bearings. After initial operation, the oiler is usually set to provide 2 drops of oil per minute. It is important that the connecting rod eccentric bearing receives adequate lubrication to avoid excessive heating and scoring of the lining. Typically, a sight feed oiler is involved. This type of oiler requires manual opening when the pump is started and manual closing when the pump is shut down. A fully automatic ball-type oiler is becoming popular. This type of oiler automatically lubricates the connecting rod bearing without manually starting or stopping. The oiler is functional as long as the operating speed is above 44 strokes per minute. Number 2. Plunger trough. A small quantity of SAE 90 gear oil in the trough of the plunger provides lubrication and increases service life. This can be added periodically to the top of the stuffing box around the packing during operation. 3. Plunger crosshead. Fill the plunger as required to cover half the pin with oil. Other points requiring regular lubrication are belt drive, chain drive or gear reducer, bearings, and motor. Again, refer to the manufacturer's recommendations for specific instructions about lubrication requirements and schedules. During operation of the plunger pump, be on the lookout for a number of conditions or problems. First is excessive wear of the plunger. Check the amount of wear on the plunger whenever the packing is changed. Refer to manufacturer's literature for allowable wear. The housing that holds the ball check valve and valve seat can also become worn with use. If the valve seat is worn, there will not be a good seal between the seat and the ball. The condition of the seat should be checked periodically and changed when necessary. Periodically, check the amount of wear on the ball check valves. Tools can be made to allow a quick check of the wear on the ball check valve. The check valve in this picture should be replaced when the entire ball fits through the hole in the PVC guide. Refer to the manufacturer's literature for requirements and limits of wear. One manufacturer, for example, allows a 16 mm 5/8 inch decrease in the diameter of a 125 mm 5-inch ball before replacement is necessary. This is about a 30% decrease in the volume of the ball. The ball check valves normally provided are made of lead-impregnated neoprene. These are satisfactory and economical for most installations. Special balls are available for use when corrosive or severe abrasive wear is encountered. Again, you will have to refer to the manufacturer's instructions. The ball check valves normally provided are made of neoprene or hypalon. These are satisfactory and economical for most installations. Special balls are available for use when corrosive or severe abrasive wear is encountered. Again, you will have to refer to the manufacturer's instructions. To prevent overheating of the eccentric, check the clearance between the eccentric and the babbitt and the rate of lubrication of the connecting rod regularly. Water hammer is another condition that should be prevented. A sudden change in the flow of water in a force main can cause a large backflow of water or a sudden surge of water into the main. This sudden increase in pressure is referred to as water hammer. Whenever the pump is arranged with a positive pressure head on the suction, or with an exceptionally long feed line, water hammer is likely. It can be controlled by the addition of an air chamber at the inlet as shown. This is the end of the discussion of the plunger positive displacement pump. Diaphragm pumps. Another basic type of positive displacement pump is the diaphragm pump. In this pump, a diaphragm provides the mechanical action to force liquid from the suction to the discharge side of the pump. The diaphragm moves up and back and forth horizontally in a chamber. As the diaphragm moves in one direction, it creates an area of lower pressure which allows atmospheric pressure to push fluid into the pump. This is the suction cycle of the pump. When the diaphragm moves in the other direction, the check valves ensure that liquid is forced out of the pump. This is the discharge cycle of the pump. Actually, the diaphragm provides the diaphragm pump with an advantage over the plunger pump. In the diaphragm pump, the material being pumped does not come into contact with moving metal parts. This can be important when pumping abrasive or corrosive materials. While there are a number of different types of diaphragm pumps available, there are three main types used in wastewater treatment plants: the air-operated diaphragm pump, the chemical metering or proportional pump, and the air-powered double diaphragm pump. This section will consider each of these types of diaphragm pumps, starting with the diaphragm sludge pump. The diaphragm sludge pump is similar to the plunger pump. The main difference is that the up and down motion providing movement of the liquid through the check valves is provided by a diaphragm instead of a plunger. Here is a diagram of a typical air-operated diaphragm sludge pump. As you can see, there are many similarities between this pump and the plunger pump. This type of pump is commonly used to pump heavy sludges or slurries. The pumps shown here are used as digester feed pumps and typically pump 5 to 7% dry solids sludge. Let us see how air is used to drive the up and down motion of the diaphragm. This is a diagram of the air-operated diaphragm pump with all of the major components labeled. During the fill stroke, the inlet valve is lifted by suction head and the fluid to be pumped fills the pump cavity. Air is allowed to exhaust as the diaphragm moves upward. The discharge valve prevents any backflow from entering the pump. During the discharge stroke, air is forced in to the pump cavity. It pushes down on the diaphragm. The pressure this creates closes the inlet valve and opens the discharge valve, allowing the fluid to discharge from the pump. As you may have noticed, fluid only enters the pump during the fill stroke if there is sufficient suction head available to push it in. If suction lift is required, a pump variation where the diaphragm is mechanically assisted must be used. We will examine spring-assisted and air cylinder-assisted diaphragm pumps. In this variation, the diaphragm is mechanically lifted by a spring-activated rod during the fill stroke. This action draws fluid into the pump. The discharge cycle is the same as before, except now when the air pushes the diaphragm down, it also stretches the spring. Spring-assisted diaphragm pumps are suitable for applications where there is 3 meters, 10 feet, or less suction lift and fluids with high viscosities must be handled. The spring action also increases the pump's capacity. In this variation, the diaphragm is lifted and lowered by an air cylinder actuated rod. With the air cylinder assist, these diaphragm pumps handle suction lifts up to 6 meters, 20 feet, and achieve discharge pressures of up to 650 kilopascals, 95 psi. Each air-operated diaphragm pump must have a source of compressed air and equipment to control it. Compressed air to drive the pumps can come from a tap off of a process air line or from a dedicated blower or compressor. The compressed air going to the pump is controlled by a solenoid valve and pressure regulator. A muffler is usually added to the air line to reduce noise. Refer to the manufacturer's literature for specific information about operation and maintenance of a certain diaphragm pump. Here are some points necessary to replace the diaphragm, check valve ball, or check valve seat. The frequency of this maintenance depends largely upon what types of materials are being pumped. Since the air-operated diaphragm pump has no seals or bearings, lubrication is typically not required. However, grease lubrication of the spring in the column tube on the spring-assisted model is usually recommended. Be sure to clean the pump every time it is used to pump material that should not harden inside the pump. This includes sludge, wastewater, mud, and chemicals. Normally, pumping clean water through the pump for several minutes will be sufficient to clean it. Before storing the pump for a long period of time, be sure to thoroughly wash all accessible parts. Before storing the pump during freezing weather, drain all liquid from the pump body to prevent ice from cracking the pump. Remove the ball valves to let the pump drain thoroughly. While the manufacturer should provide you with more detailed information, here is a general troubleshooting guide for the diaphragm sludge pump. Problem: air regulator vents excessively. This occurs when dirt gets into the regulator valve or the operating air pressure is too high. To correct the situation, clean and lubricate the valve or reduce the air pressure. Problem: air in discharge line. Possible cause: ruptured diaphragm. Problem: excessive pipe vibration and water hammer. The possible causes include the air pressure is too high, the air chambers are not working, or a piping support is loose. To remedy these, reduce the air pressure, clean the check valves, or charge the air chambers. Problem: the pump will not pump at all or pumps below capacity. The ball valves might not be seating properly. Clean debris from them or replace worn parts. Also, the diaphragm may be loose or worn. If so, tighten the bolts on the clamping ring or replace the diaphragm. Chemical metering or proportional diaphragm pump. Another common type of diaphragm pump is called the chemical metering or proportioning pump. As the name implies, this type of diaphragm pump is often used as a chemical feed pump. Here is a picture of a typical chemical metering pump installation. The chemical feed pump may be driven directly, as the one shown in this picture, or by a belt drive. Further speed reduction may be provided by worm gear reducers. This diagram identifies the major components of the belt-driven chemical metering pump. This unit operates as follows. The belt from the motor turns the pulley, which is connected to the worm gear. This causes the other gear to rotate, which drives the eccentric. Rotation of the eccentric pushes the diaphragm to the left on the power stroke, and a spring pushes the diaphragm back on the suction stroke. The flow of liquid through the suction and discharge valve is similar to that described for other pumps. With this pump, however, the ball valves must be in a vertical position to operate properly. The feed rate can be controlled in two ways. The feeder can be equipped with two 3-step pulleys. Changing the belt from one step to another will change the rotation of the eccentric, changing the number of strokes per minute. The length of each stroke can also be altered with a feed rate control knob. This method pushes a wedge against the rod pushing the diaphragm, shortening the length of the stroke. The pump must be operating to adjust the feed rate. Operators may be required to set up a chemical metering pump in the plant, so it is important to know chemical metering pump assembly requirements. This diagram shows a typical installation. Note the following. The suction line should be just long enough to keep the foot valve and strainer in an upright position at the bottom of the solution tank. To ensure a full suction line to the pump, the chemical feed pump is often located below the minimum liquid level of the supply tank as shown. When the pump is below the supply tank, siphoning action will keep liquid flowing even when the pump is not running. To prevent this siphoning action, add an anti-siphon spring to the discharge valve, as shown in the diagram. When the pump is running, the valve will open because of the pressure caused by the pumping action. When the pump stops, there is no pressure. The spring closes the valve so that there can be no siphoning of the solution through the valve unless the spring is not strong enough to push the valve shut. As with other equipment in your plant, refer to your manufacturer's literature for specific operation and maintenance instructions for each chemical metering pump. Here are some. The supplier's literature should indicate how new equipment should be installed. To ensure that the equipment is properly set up and operating, here are things to check when examining newly installed equipment. 1. Is the pump mounted in the proper upright position? If the pump is not mounted properly, gears may not lubricate properly, and the pump might fail. 2. Are the suction and discharge valves vertical? The valves will only work when they are vertical, and the valve seat is at the bottom. 3. Are the suction and discharge lines installed properly? The suction line should run as directly as possible from the solution tank to the pump. There should be no sags or low spots in the line, because these could cause air locks. Here are some general points to consider every time the system is restarted. The method of selecting the stroking rate will depend on the equipment. If pulleys are involved, lock out and tag the motor before moving the belt onto the correct pulley to obtain the feed rate required. If a knob is provided for fine-tuning, it should be turned only when the unit is running. Open all valves in the suction and discharge line. Remember never to run a positive displacement pump against a closed discharge valve. If the pump is located above the supply tank, priming may be required. Without lifting the foot valve out of the solution, move it up and down quickly. This will make the foot valve lift and will force liquid into the suction pipe. Keep on doing this until the solution moves into the pump head. When the pump head is filled and the solution has reached the discharge valve, the pump is ready to start pumping. Be sure that there is enough solution in the tank before the pump is started. Check the suction lines and connections for air leaks or pockets of air and eliminate them. If the pump has an automatic level control system, check it to be sure that the pump turns on and off at the set levels. If water is used to prime the pump, be sure to add the appropriate amount of chemicals to the feed tank. Adjust the chemical feed rate with the control knob when the pump is operating. Most equipment manufacturers give graphs or tables that give the feed rate for each setting of the control knob. Calibrate the pump yourself by measuring the volume delivered in a certain period of time at various control knob settings. When making adjustments to the feed rate, be sure to follow the manufacturer's instructions. If a knob is involved, never use force to move this knob. The pump will be damaged if you do. A sign placed near the pump will serve as a reminder of this point. Air-powered, common type of diaphragm positive displacement pump is referred to as the air-powered double diaphragm pump. As the name indicates, the pump uses an air supply such as this to power the pumping action. The air-powered double diaphragm pump is normally used to pump sludge or chemical slurries. Here is a picture of a typical installation. A series of diagrams here will illustrate how this pump works. Note that in each of the two chambers there is a diaphragm, clamped at points A to the pump body. The two diaphragms are connected by a shaft, which makes both diaphragms move simultaneously. The pumped liquid is in the outer pan of each diaphragm chamber. Liquid flow is controlled by the inlet and outlet check valves. In this particular diagram, the valves are shown as ball check valves, but flap-type check valves could be used as well. The two inlet valves are connected through a manifold to a common inlet. The same occurs at the outlet. The air valves are important to the operation of this pump. In fact, the air valves control the entire operation by alternately pressurizing the inside of one diaphragm chamber and exhausting the air from the other one. The compressed air enters at point A and is directed by the air valve alternately into chamber 1 and into chamber 2. In the diagram, air has been directed into chamber 1. This pushes the diaphragm to the right and moves the slurry through the open ball valve at 3 to the outlet. The ball valve at 4 is being pushed shut. Keep in mind that there are other things happening in the other side of the pump at the same time. The shaft pulls the diaphragm in valve chamber 2 to the right. This pulls valve 6 against the seat and closes it. Valve 5 is opened and the slurry is sucked into the valve chamber. The air that is forced out of valve chamber 2 comes out of the exhaust. To understand this pump, remember that the air valve shifts the air supply to both diaphragms alternately. When air is being supplied to valve chamber 2, both diaphragms move to the left. This forces air out of valve chamber 1 into the exhaust. Valves 4 and 6 are open, and 3 and 5 are closed. Slurry is being pumped from the left chamber. When the pressurized diaphragm reaches the limit of its stroke, the air valve shifts the air supply to the opposite diaphragm. As with other equipment, refer to the manufacturer's literature for specific information about operation and maintenance of the air-powered double diaphragm pump. But there are some general considerations to point out. The operator will be responsible for cleaning and tightening valves and fittings. At least every 6 months, everything including the diaphragm should be checked, cleaned, and replaced if necessary. Remove any old Teflon tape used to help seal valves or fittings that are being replaced. Apply new tape and then finger tighten. Do not use wrenches to tighten plastic fittings. Forcing a plastic fitting can damage it. It may be necessary. Operators may also need to replace the diaphragms from time to time. Replacing the diaphragm is not difficult, but an equipment manual will be helpful. To install a diaphragm, first remove the pump head. Run the pump at its slowest speed, and turn it off when the diaphragm is farthest out from the pump housing. Follow the standard lockout-tagout procedure, and be sure to lock out the air supply to the pump. Make sure to replace the pump head with the discharge valve on top, and the head in the vertical position. Also be sure to tighten the pump head screws evenly. While the pump manufacturer should provide more detailed information, here is a general troubleshooting guide for the air-powered double diaphragm pump. Problem: no feed. Probable cause: it may be air-bound, in which case loosen the discharge line to vent air. For acid pumps, open the bypass. Set the feed control to maximum. The cause may be air leaks. For this, tighten all suction line joints. A blocked line will also prevent feed. Clean the blockage by cleaning the foot valve, suction line, and suction check valve. Or, if there are leaking check valves, remove, inspect, and clean the valves. For ball check valves, the seat must be at the bottom. The diaphragm may be broken. Remove the heads to inspect them. Replace any damaged parts. If the pumping rate of the pump is too high, the fluid might be siphoning through the pump. This can be fixed by installing an anti-siphon valve. Progressing cavity pumps. Another basic type of positive displacement pump commonly used in wastewater treatment plants is the progressing cavity pump. In this type of pump, a rotor and a stator provide the mechanical pumping action. Progressing cavity pumps are used to pump materials with very high solids content. Small progressing cavity pumps are normally used to pump chemical slurries. Large ones pump sludge. Here is a cutaway view of a progressing cavity pump. The major components are labeled. Note the following points. The drive shaft can either be hooked up directly to a motor, or it can be driven by V-belts and pulleys, or by chains and sprockets. The seal may be either standard packing or a mechanical seal, similar to those in other pumps. Now, let's see how it works. We'll follow a series of diagrams to illustrate the principle of operation of the progressing cavity pump. In a progressing cavity pump, the material pump travels in the space between the rotor and the stator. Look at the cavities in the diagram highlighted in yellow. In this diagram, the rotor is in the uppermost position. It creates a full cavity in the lower center and half cavities on each end. In this diagram, the rotor has moved through 1/4 turn. The cavities are now at the top and bottom, and they are progressing towards the discharge end. After a further 1/4 revolution, the rotor is in its lowest position. This creates a full cavity in the middle upper part. The cavity from the first diagram has moved its contents to the discharge end. A universal joint is located between the drive shaft and the rotor, so that the location of the rotor within the stator can be changed. The design of this universal joint varies with the manufacturer. Let's take a look at the major components of the progressing cavity pump. This diagram labels the inlet, discharge, pump body, and drive shaft. This is an end view of the pump showing the rotor inside of the stator. Here, the stator has been removed so that the other end of the rotor can be seen as well. While it is important to refer to an individual manufacturer's literature for specific operations and maintenance instructions for progressing cavity pumps, there are some general comments we should point out. The progressing cavity pump must never be run dry, because the friction between the rotor and stator will quickly damage the pump. For this reason, it is normally better to have flooded suction. In suction lift applications, the suction housing should be filled with water prior to starting the pump. A full pipe sensor may be used to shut off the pump if the suction side is dry. To prevent damage to the pump from dangerous pressure buildups, a similar high-pressure cutoff could be used. The packing gland must be adjusted to allow for a small amount of leakage. Refer to the discussion on centrifugal pumps for information on gland adjustment, packing replacement, and other relevant packing gland information. Note that if air is allowed to leak into the pump body through the packing gland, the pump may lose its prime. The stator and rotor should be checked periodically for wear. To do this, measure the crest-to-crest diameter of the rotor. When it equals the minimum operational diameter given in the manufacturer's literature, it must be replaced. The stator should be inspected for pitting and gouging and replaced if necessary. The stator should also be replaced if the rotor slips out too easily. Proper cleaning is especially important. The coupling can be damaged by rags and debris. Material that hardens between the rotor and stator will cause problems. Grit will cause excessive wear on the rotor and the stator. Flush the pump anytime it is stopped for a period of time. More elaborate cleaning is required for long-term storage, and may be necessary to add a flushing water connection, as this is often overlooked, but necessary provision. Mechanical seals, bearings, couplings, motors, valves, and other components require regular maintenance. Be sure to refer to the earlier discussion in this course and to manufacturer's literature. As a source of information and reference, a troubleshooting guide for the progressing cavity pump follows this section. Remember to always lock out the pump before performing maintenance on it. The pump will not pump when the motor is running. The belts could be slipping. For this, tighten the belt and apply belt dressing if necessary. The pump may not be pumping because the rotor is initially tight in the stator from sitting idle. To ease it, turn the pump manually 2 full rotations. First, disconnect the power to the drive. Lock out and tag, then disconnect couplings or loosen the belts. Then grip the drive shaft head with a suitable wrench and turn, being careful not to damage the shaft. Problem: there is no flow. Probable cause: there is an obstruction in the suction line. Make sure all of the valves are open. Or there may be a loss of suction in suction lift applications. Check that air is not leaking into the suction housing by way of the packing gland. An inadequate amount of grease or low pressures in water flush systems will allow air to enter the suction housing. Also check the piping system for problems. Collection of debris in the suction housing may also stall the flow. In this case, stop and lock out the pump. Drain the suction housing, open the inspection plates, and remove the debris. The pump may be operating in the wrong direction. Have an electrician reverse the rotation of the drive. If there is an absence of fluid to be pumped, check the fluid level controls. Repair them if necessary. Problem: excessive noise and vibration. Probable cause: the suction or discharge valve may be closed. Make sure all of the valves are open and there is adequate flow to the pump suction. The driver and pump may be out of alignment. Check that all pulleys are mounted and aligned onto the shafts, and the belts are properly connected. Make sure the couplings are firmly connected. Or the pump may have loosened on its mounting. For this, tighten the bolts or add grouting to the foundation. If the pump body and stator support are loose, tighten all loose bolts on the supports. Noise and vibration may also occur if the bearing housing stator and suction housing are out of alignment. In this case, make sure all bolts on these sections are tightened to the proper torque. Or, there may be air in the pump body. For this, add water through the suction line. Problem: the bearing housing becomes hot, 160 degrees Fahrenheit, 70 degrees Celsius, or more. Probable cause: the bearings have been over-lubricated. For this, remove the relief plugs in the bearing and run the pump for a short time. Then replace the plugs. Or, the bearings may need grease. Add grease through the fitting. Another cause of heat is that the bearing grease has become contaminated with water or sludge. Inspect the grease by removing the bearing cover plates. If it is contaminated, replace the grease after removing the shaft assembly and cleaning the bearings. Clean, inspect, and replace the bearings if necessary. Heat will be generated if the pump and drive are not aligned, in which case realign the pump and drive. Problem: there is low flow. Probable cause: the viscosity of the fluid or suction lift is higher than expected. This can be remedied by enlarging the pipe size or increasing the speed of the driver. There may be low flow because solids have settled in the suction housing or line. For this, stop the pump, drain the suction housing, and remove the debris through the inspection plates. Clean inside pipe walls and elbows. Or, belts may be slipping. Replace old and worn belts. A worn rotor or stator is inefficient and can slow the flow. In this case, replace one or both. To check the wear of these items, disassemble the pump. Measure the crest-to-crest stator diameter and compare it to the manufacturer's specifications. Check the stator for gouging and the rotor for looseness. Screw pumps. Another type of positive displacement pump used in wastewater treatment plants is the screw pump. In this pump, a large screw provides the mechanical action to move the liquid from the suction to the discharge side of the pump. This photo shows an enclosed screw pump installation. This particular plant uses large screw pumps to pump all of the wastewater flow to the secondary treatment process. Here is another example of screw pumps, where the screw flights are enclosed in a steel cylinder. This picture shows a plant in which the covers over the screw pumps have been removed. Screw pumps are used in applications where fluid does not have to be raised very much. This diagram will help demonstrate how the screw pump works. In this example, the wastewater enters the wet well from the left. Rotation of the screw carries the wastewater up the incline and discharges it into the channel at the top. Adding a bit more detail to the same diagram, note the filling point, the touch point, and the delivery point. The elevational distance between the fill point and the delivery point is the lift of the pump. The filling point is the water level at which the screw pump reaches its peak efficiency. When the water level drops below this point, the volume pumped and the efficiency are reduced. However, the screw pump will continue to move fluid as long as there is enough fluid in the wet well to submerge the lower end of the screw flight. Note too the support points labeled A and B. The screw does not touch the incline, but it is important that the clearance between the screw and the channel be at a minimum. The channel in which the screw turns can be made of metal or concrete. Typically, concrete channels are used only with larger screw pumps. For enclosed screw pumps, the screw rotates within the rotating or stationary outer tubes. Greater slopes can be achieved with enclosed screw pumps. The diagram illustrates one way in which the capacity of screw pumps can be varied. These are known as single, double, and triple helix flights. Screw pumps also vary in size. The diameter of a screw pump can be as little as 0.3 meters, 1 foot, or up to 3.66 meters, 12 feet. Here are some other characteristics of screw pumps. Most screw pumps rotate in the 30 to 60 RPM range, although smaller screw pumps are faster. Open screw pumps can be designed for slopes of approximately 20 degrees to 40 degrees. The most popular slopes are 30 degrees or 38 degrees. Enclosed screw pumps can achieve slightly higher slopes, up to approximately 45 degrees. The maximum lift for large diameter pumps is about 10 meters, 33 feet. Small diameter pumps have lower lift capabilities. To determine the capacity of the screw pumps at a plant, consult manufacturer's literature. Now let's take a look at the drive assembly for the screw pump. The picture shows the shaft at the end of the screw. The covered coupling, the gear reducer, and the caged V-belt and pulley system are labeled. This is only one type of drive assembly. Other methods of connecting the motor to the screw pump are also used. To end the discussion on the screw pump, let's look at the bearing. The arrow in this picture points to the approximate location within the housing of the upper bearing. This bearing carries the weight of the screw and absorbs the thrust of the pumping action. There is a lower bearing as well. The lower bearing for the enclosed screw pumps located above the water level is under a protective cover. The lower bearings for open screw pumps, shown in this cutaway section, are sealed automatically. Grease-lubricated bearings submerged in the liquid to be pumped. Check with each manufacturer to determine the exact maintenance requirements for the equipment. Peristaltic pumps, another type of positive displacement pump that can be effectively used at wastewater treatment plants, is the peristaltic pump. These pumps are used to pump sludge and for chemical metering. Fluid is moved through the pump by the movement of the rotor as it passes over the internal hose. A light oil lubricant is placed in the housing to reduce friction between the rotor and the hose. Some advantages of this design are that the fluid being pumped does not contact any of the pump's moving parts. Accidentally running the pump dry will not cause damage. The pump is self-priming, and it can handle corrosive chemicals and abrasive slurries. Peristaltic pumps are now available to handle very low flows, such as chemical metering, up through 13 liters per second, 200 gallons a minute. The pump can pump pressures greater than 1,350 kilopascals, 200 psi. The fluid being pumped only comes into contact with the inside of the internal hose. Therefore, it is very important that the hose material selected is appropriate for the fluid to be pumped. The hoses are made of cloth-reinforced, thick-walled rubber. The type of rubber should be selected based on the corrosiveness, the abrasiveness, and the temperature of the material to be pumped. While it is important to refer to an individual manufacturer's literature for specific operations and maintenance instructions for peristaltic pumps, here are a few general comments on maintenance. Replacing the internal hose is the most common maintenance operation on a peristaltic pump. This video demonstrates the procedure. It is important to regularly check that there is adequate lubricant in the pump housing. Manufacturer recommendations are usually to keep the housing 40 to 50% full. Visually check the shaft bearings. If the bearing appears to be contaminated, add new grease to flush the bearing. Rotary lobe pumps are another type of positive displacement pump that is suitable for pumping sludge. Rotating lobes are synchronized so that they will remain in contact continuously. This action carries the fluid through the pump, similar to the operation of the progressing cavity pump. Depending upon the fluid being pumped, the lobes can be made out of various metals or hard rubbers to get maximum wear. One advantage of rotary lobe over progressing cavity is that it is cheaper to replace the lobes than it is to replace a rotor and a stator. As with other positive displacement pumps, severe damage or even dangerous conditions can result if a rotary lobe pump is operated against a discharge line that is blocked or restricted. It is a good design practice to include a discharge pressure gauge and a pressure switch to shut down the pump if high discharge pressures occur. Since the operating principles are very similar, the troubleshooting guide already presented for progressing cavity pumps also applies for rotary lobe pumps. Airlift pumps. The basic types of positive displacement pumps commonly used in wastewater treatment plants were discussed in this course. These are the plunger pump, the diaphragm pump, the progressing cavity pump, the screw pump. Rotary lobe pump and the peristaltic pump. This last section will discuss the airlift pump. While the airlift pump is not a positive displacement pump, it is used in wastewater treatment plants. This course includes it here to complete the discussion of pumps commonly used in treatment plants. The airlift pump uses compressed air to move the liquid from the suction to the discharge of the pump. Airlift pumps can be used to pump wastewater and thinner sludges up to heights of 1.5 meters, 5 feet. Here is a diagram of a typical airlift pump installation. Compressed air is forced into the eductor pipe through an air injector. The air bubbles mix with the wastewater, creating a less dense mixture that will rise. This upward flow creates an area of low pressure in the eductor pipe, which allows atmospheric pressure to push the fluid into the tailpipe, setting up the pumping action. The rate of flow is controlled by how much air is forced through the injector. The rate of flow also depends on the depth of the air injector below water level. The deeper the injector, the more liquid will be pumped. Since airlift pumps need an air supply, they are often used in activated sludge plants to pump side streams. The same blower that supplies air to the aeration tank provides the air for the airlift pumps. While this dual usage of the blower is convenient, there can be problems. First of all, there may not always be sufficient airflow available for both the treatment process and the airlift pumps, especially under peak loading conditions. If the air injector is above the level of the diffusers in the aeration tank, the air used for pumping will meet less resistance than that for aeration. Most of the air then will go through the airlift pump and could result in too little air for the aeration tank. The air supply valve in the diagram must be adjusted with regard for both the pumping rate and aeration requirements. With more complex systems, however, valve adjustments may not be sufficient to correct pump function and further investigation may be required. Conversely, if the air injector pipe is lower than the diffusers, the airlift pump may not get enough air. This can be corrected by raising the air injector or throttling the air supply line to the diffusers or isolating the two supply lines. In the diagram, there's a shutoff valve at the top of the airlift. Never throttle the discharge when the pump is operating. This shutoff valve is not used to control the flow rate through the pump. Rather, the shutoff valve is used to backflush the airlift pump if there is a blockage in the tailpipe. Closing the shutoff valve forces air down the tailpipe, dislodging solids that are stuck. If backflushing does not work, then the airlift must be rotted. In the examples we have used so far, we have seen one type of airlift pump. There are many arrangements possible. Another piece of equipment based on the same principle as the airlift pump is the airlift skimmer. The airlift skimmer can remove scum from the surface of a settling tank using the same principles as the airlift pump. Floating collars or rings help keep the inlet close to the water surface, which ensures that scum is collected from a larger area. As the diagram indicates, the airlift surface skimmer is a vertical U-tube. One end of the U acts as the scum inlet. The other end has an air connection. To work properly, the scum inlet has to be at the right depth. Adjusting screws are provided on the inlet for this purpose. Or, a floating collar can slide up and down to get the right depth. Before the discussion on the airlift pump closes, here is some troubleshooting information for the main operational problems that occur with an airlift pump. Problem: airlift performs erratically. Probable causes and remedies. Verify that the depth of submergence of the air injector is sufficient. We will demonstrate with a sample calculation. Also, the airlift pump may be receiving an inconsistent airflow rate because of aeration tank air requirements. Rework air supply piping to isolate pump and diffuser supplies. The height to be pumped is the distance between the liquid level and the height at which the liquid is discharged. Suction friction losses also have to be considered. In this example, suction friction losses are almost zero because the fluid enters the pump just below the air injector. If the airlift is performing erratically, check the percent submergence using this formula, where S equals depth of air injector submergence, H equals height that the liquid must be pumped, F equals suction friction losses. In order for the airlift to function properly, This ratio must be greater than 0.7. This ratio is referred to as the percent submergence. Here is an example of the calculations that are performed to determine the percent submergence. Assume that air is injected at a depth of 2 meters, 6.5 feet, into the surface skimmer. The height to be pumped is 0.5 meters, 1.6 feet. In metric units, the values for this example would be S is equal to 2 meters, H is equal to 0.5 meters, and F is calculated to be 0.3 meters. In English units, S is equal to 6.5 feet, F is equal to 1 foot, and H is equal to 1.6 feet. In this case, the percent submergence is less than 0.7. This means that the airlift pump will likely give erratic performance. If the airlift pump has just about stopped pumping, expect a problem with the air supply or clogged suction line. Check the air supply line for leaks or obstructions. Check the sensor that starts the blower when low air pressure is indicated. Check the blower as well. If the suction line is clogged, close the shutoff valve so that the flow of air will be through the suction line, as shown in the diagram. This is often enough to dislodge particles stuck in the line. If this does not work, remove the top of the T and rod the line. This ends the part of the course dealing with positive displacement pumps.